A very important category of functions is ones where, as x gets closer to 0, the function turns into a fraction, or is a fraction, and then both the numerator and denominator individually both approach 0. And, it comes down to the question is, when you see 0 over 0, what is it? Well, maybe it equals 1, because the zeros cancel out, because that's one rule of math, that if the numerator and denominator are the same, fraction equals 1. Or maybe it equals 0, because any fraction with the numerator of 0 is 0. And maybe it equals infinity, because if the denominator is 0, the fraction usually becomes infinity. Or maybe it becomes something else altogether. And the answer is that any of these four things are possible depending on the situation. The most basic situations we can answer already from the last video. Like if I say x squared over x. Let's say that's our function, f of x equals. Well, you can't say, what is f of 0, because f of 0 itself, if you put 0 in, you get 0 over 0, which is undefined. So we don't ask what's f of 0. I mean, we could ask it, but it's going to be undefined. But instead, we could ask something that seems like the same question, which is, what is the limit of f of x as x approaches 0? Which is the limit. In the last lesson, it was a lot of x equals x approaching infinities, but now it's x approaches 0. If your expression is just a simple, like a times x to the n power, and the denominator is also something like that, and there's not other stuff going on, then you can just reduce the fraction. And then you can plug 0 in, because now the denominator is no longer becoming 0 because it became a constant. So in this situation, the answer would be 0. If instead of writing f of x, I'm going to just write another expression. If it was x over x squared, so that's another 0 over 0 situation. But if you're able to reduce that fraction, and after reducing the fraction you get a constant in the numerator and a variable in the denominator, then it's going to be infinity. And if I have something like this, that's also a thing that if you try to plug 0 in, you get 0 over 0. But if you cancel out, reduce the fraction, whoops, that's 0. So the limit of a constant function doesn't matter what it's going to. It's going to be 2/3. So those are three situations where we have 0 over 0 kind of, at least from a limit point of view, becoming 0. Becoming infinity, becoming something else. But there are some more complicated expressions also. So here I want to do about 5 different ones. So here's a function that looks really contrived, but something like this is going to come up a lot in future lessons. So here's a function, 5 plus x squared minus 5 squared over 5 plus x minus 5. And if you try plugging 0 in, you would get 25 minus 25 over 5 minus 5, which is 0 over 0. So we can't really work with that because we don't 0 over 0 itself could be a lot of things depending on the situation, and we'll see which situation this is. So I'm going to say the limit as x goes to 0 of 5 plus x squared minus 5 squared over 5 plus x minus 5. Instead of just plugging 0 in, I'm going to simplify the numerator and denominator. The denominator just ends up becoming x because the 5's cancel out. The numerator, this becomes 25 plus 10x plus x squared. And this 5 squared becomes 25. So we get 10x plus x squared. Now that's a 0. That's still 0 over 0. But we can go a little further now because I can, in the numerator, I can factor out an x. And then I can cancel out the x. And now suddenly it becomes something. The limit as x approaches 0 of 10 plus x. Well, that is something I could just plug 0 in for x, and I don't get a 0 over 0 situation. And I get 10 as the answer. And this pattern comes up a lot in higher math. If it was almost the same question, but instead of squared, that's plus, instead of squared, it's cubed. Now the denominator still becomes x. The numerator becomes, well, with binomial expansion, raising to the third power can be pretty complicated. So we would get 125 plus 3 times 5 squared plus x, which is 75x, plus, I should say, 15x squared. And there's going to be other terms, although I'm not going to write them right now because I'm going to put this minus 125 here, and I'll show you why it's not necessary for me to so in such detail to expand the entire numerator. Because what ends up happening is that this is a minus 125. These cancel out. Oh, I just realized something, if you don't mind. When I expand this thing, since this is 5 plus x, not x plus 5, it would be 5 cubed. Remember from Pascal's triangles, 1, 3, 3, 1 are the coefficients. 3 times 5 squared x plus 3 times 5 times x squared plus x cubed. So I do want to do that. So I do want to have 75x here. So I'd have the 75x, this x is in the denominator, and there would be other stuff. And it actually doesn't matter that much about the coefficients because when you split this thing up, you would get, when you take each piece of the numerator and sort of split up this up to 75x over x plus whatever x squared over x. The reason why it wouldn't matter, I should keep writing limit as x goes to 0. This 75x over x, the x's would cancel out, whereas in these other things, you'd have an x squared over x, so even though you canceled out the x, you'd still end up with an x on top. Let me clean this up a little bit. So we'd end up with limit as x approaches 0 of 75 plus limit as x approaches 0 of something x plus limit as x approaches 0 of something x squared. And all these things would become 0, and all that will be left is the 75. So if you can anticipate that there's going to be a lot of terms with x to powers greater than 1, those terms aren't going to be important because they're going to end up becoming zeros anyway. And the answer to this question was just 75. So again, if you just plug 0 in right away, you get 0 over 0. That could be almost anything. In this case, it's actually 75 is more accurate. And this is not saying that f of 0 equals 75. That's not what this is saying. It seems like it's saying that. It's saying the limit as x approaches 0 of f of x equals 75, which is not exactly the same question, although it is similar. So here's a more complicated function. It's less complicated because it doesn't have the exponents in it, but it's got these fractions. So here's a function, and if you try to do f of 0, you would get 1/3 minus 1/3, which is 0, and 3 plus 0 minus 3, which is 0, so you sort of can't work with that. So we don't ask what's f of 0. We ask what's the limit as x approaches 0 of f of x, which is 1 over 3 plus x minus 1 over 3 over 3 plus x minus 3. Well, the way we do this one, denominator is easy. That's just x. For the numerator, I'm going to combine those fractions with common denominators. So the common denominator is going to be 3 plus x times 3. And this numerator is going to become 3 minus, and the numerator for this one, over here I'm going to need the 3 plus x. And I really should be continually writing lim x goes to 0, but I'm going to just have it implied there. So the numerator ends up becoming negative x. Remember to distribute the negative through, over 3 plus x times 3 over x. Well, this x could actually, down here, could cancel out with this one, but if it's not obvious to you, you can write it like this, and then cancel out. Don't forget this negative sign. So we end up with negative 1 over 3 plus x times 3. This limit x approaches 0 is still here. Finally, I could plug 0 in. And then I don't get 0 over 0, I get negative 1/6, which is the answer to that question. Okay, here's another one. This one involves square roots. Again, notice that if you try to put 0 in, f of 0, you'd end up with 0 over 0. Root 3 minus root 3 over 3 minus 3. But that doesn't mean there's not an answer to this question. Limit as x approaches 0 of f of x. Well, the denominator becomes x, but the numerator is not obvious how to simplify, because even this, if you put 0 in for x, you get 0 over 0. So the trick to this one, remember rationalizing the denominator? Well, how about rationalizing the numerator? You're going to need a plus there. Now, we've never had any need to rationalize the numerator, and it's not even that obvious that this is going to lead us anywhere. But I promise you that if you do rationalize the numerator, the denominator becomes this, radical 3 plus x plus radical 3. And the numerator becomes radical 3 plus x times radical 3 plus x is 3 plus x. This is like a difference of perfect squares things. So the outer and inner cancel, and we end up with minus 3. And those cancel out. And while we're at it, now we have x and this x, they cancel out also. And we have a 1 on top. Well, we can plug 0 into this thing. and we get 1 over radical 3 plus radical 3, or 1 over 2 root 3, which is the answer to that question. Maybe you've noticed that all these examples have the same sort of form where the denominator is like a constant plus x minus the same constant, and the numerator is like its own function, in this case sine of something plus x, and then minus sine of that same thing, of the first thing. Now, this is another one that if you try to do f of 0, you would end up with 0 over 0. But instead, we're going to do the limit as x approaches 0. And for this, well, the denominator turns into x just like it has for all of these. But the numerator, the way to do this is to use the sine a plus b formula, which is sine a cosine b plus cosine a sine b. I still have this sine pi over 6 here. Now I can do a little more with this algebraically. I'm going to put these two things next to each other and factor out the sine pi over 6. So I get cosine x minus 1. And I'm also going to split these guys up, so like I'm going to put this in its own term. Well, this may all look nice, but when you plug in 0, you're still getting 0 over 0 for both of these fractions. But to finish this up, I'm going to tell you two facts that I'm not going to prove. You learn them in calculus next year. One is that the limit as x approaches 0 of sine x over x. So as x gets really small, here's like a picture of a sine curve. And here's a picture of y equals x. And for very small values of x, this little area right here, the sine curve is almost on top of this line. So for very small values of x, limit of sine x over x, equals 1. And another fact I'm just going to kind of tell you, the limit of cosine x minus 1 over x, even though if you actually plug 0 in, you'd get 0 over 0, cosine x minus 1 over x actually gets closer and closer to 0. You could verify these by putting your calculator into radian mode and doing sine of like 0.001 over 0.001, and you will see that it's going to be approximately 1, whereas cosine 0.001 minus 1 over 0.001 is going to be close to 0. So these are just two things, not proved. Each of these things on their own gets proved in calculus. But for now, let's just say those are two things that people have figured out. So if you believe those two things, then this sine x over x can be replaced with 1, and this cosine x minus 1 over x can be replaced with 0. And then the 0 times the sine pi over 6, that whole thing becomes 0. And the only thing that's left is cosine pi over 6, which happens to be, in this case, we know is radical 3 over 2. So that was a really hard one because it did require these two sort of facts that each of them would require its own video to prove, but they are true. You can verify with your calculator. Okay, that's going to do it. So you've seen today 5 different situations where you can calculate out limits that seem to become 0 over 0, but when they're all done, they all actually become numbers. Better not undefined.